about 2 o'clock?
Yeah, it's 2 o'clock.
I got 2.
Hi. All right, so if you look on the giant screen behind me, you will probably see that we have an SI schedule now. It's also written on all of the chalkboards. There's an SI session on Sunday in the Wade Tutoring Room from 6 o'clock to 7:30, and that's Srav. And there's a session on Monday from 8:30 to 10 at night in Guilford 323 with me, and a session on Tuesday from 4:30 to 6 in Bingham 103. Bingham's the building at the end of the quad. Like if you go in the direction of Veal, there's a building facing you. That's Bingham 103. And all of us together every Wednesday have a session from 7:30 to 9 in Rockefeller 301. So if you want to do chemistry outside of class, because I know everyone likes doing chemistry outside of class, you should come to SI sessions. I think so.
Something to say. All right, folks. First of all, the seminar yesterday, if you were here, thank you very much. If you were not, Media Vision is having some technical difficulties that they are aware of, and they are working on it. No, the seminar was not simply 2 minutes and 45 seconds long, which is what is currently on Media Vision. So that will be fixed sometime today. I'm not sure when, so they're working on that. Second, I got a wonderful email from 2 of you today. I hope the 2 of you do not mind if I quote liberally from it. If you do, you shouldn't have sent it to me. I'm just kidding. Let's see. We'd have to say that we are a little offended at the end of class on Wednesday. We are figure skaters and have been doing it for several years now, and we like to think we know quite a bit about the sport. Remember, I am a hockey player. Figure skaters are, they ruin the ice with those toe picks. I'm just kidding. But I did play hockey for a number of years. And the letter goes on to tell me how they were offended, and I like the ending, by the way. I'm not offended by the letter in the least. They take offense to the fact that I said you could laugh at hockey players because they skate on double runners. So do figure skaters. Contrary to what they say in their email, all skates are sharpened with 2 edges. Figure skaters like to say 4 edges, but as it says on the website they referred me to, that's just counting the outside and the inside of each of the 2 edges on the sides of the blade. To me, that's 2 edges, but that's a debatable point. It goes on, though, and gives me a great reference to a web page that says, whoops, wrong button. Here, I'll figure out how to use this technology. The theory of ice skating is all wet. This is Google's a wonderful resource. If you haven't learned that yet, you will. Water has many unusual properties. One is at low pressure. The solid form has a volume per mole. You know what? I almost asked a question on an exam once that said, the density of solid water is X, the density of liquid water is Y. How much of an iceberg is below the level of the water? And everybody says, huh? What? It was on your physics exam. The answer is 90%. Because the density of liquid water is 90% of the density of solid water is 90% of the density of liquid water. So when you do the ratios, you find out that 90% of the volume of an ice cube is below the level of the water. Well, an iceberg's just a big ice cube. Anyway, go on from all this other stuff. Le Chatelier's principle, who cares? It is often claimed, paragraph 2, that one can skate on ice because the pressure of the skate causes the ice to melt, thus dramatically reducing the friction between skate and ice. You can do the calculation and you find out that the pressure of a 75 kilogram, slightly smaller than me, skater is going to exert about 12 atmospheres of pressure. Well, 12 atmospheres of pressure on that graph that we showed you the other day is nowhere near enough to lower the temperature of freezing of water significantly so that I can skate at 0 degrees C. Yes, I'm old enough. I did not skate indoors as a kid. I actually skated outside in Minnesota in the wintertime. It was fun. We had an ice rink in the backyard. Anyway, so if that's the case, how the heck do you skate? What is responsible? This last paragraph is great. What is responsible? We don't have a complete understanding of why ice skating works. It is likely partially related to an effect known as surface melting. What the heck is surface melting? The stability of solids is due to the regular structure that allows for each molecule to have multiple attractive interactions. Remember the sodium chloride crystal? Sodium ion, chloride ion, sodium ion, chloride ion. What if I'm at the edge? of a sodium chloride crystal. Oh, do I hear a phone I need to answer? I thought I heard a phone. Anyway, what's on the edge of a sodium chloride crystal? Well, there's sodium ion, chloride ion, sodium ion, chloride ion. But if you look in the other directions, when you look down from the sodium ion, there's a chloride ion. When you look down from the chloride ion, there's a sodium ion. What happens when you look up? There's nothing. And so the sodium and chloride ions on the surface of a sodium chloride crystal are going to behave differently than the sodium ions and the chloride ions within the bulk of the crystal, in the middle of it. The same is true of water. Water molecules in the middle of an ice cube behave differently than water molecules on the edge, because the attractive force of the water molecules in the middle is governed by all the water molecules around it. On the edge, you lost half your dimension. And so those things up on top are going to behave differently. So it goes on to say, blah, 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 blah. At the surface of solid, this is not the case, since there are no molecules above the surface to bind to. As a result, the surface molecules will often distort to make the best of a bad situation by trying to increase their bonding to each other and those below. This is known as surface reconstruction. It is also known that the molecules on the surface can become disordered and liquid-like at temperatures below the normal melting point of a solid. So yes, you do get a layer of liquid underneath the skate blade, but it's not because of pressure, it's because of the attractive forces of the forces of attraction between different molecules. And because the surface is going to have different attractive forces, it's going to behave differently. Now, if you go on and you keep going through this site, there's only 3 questions on this page, but I wish this guy had done more writing. Ionic solutions don't look like that. We talked about this the other day in class. When you put sodium chloride into water, what happens to make it dissolve? Well, why does sodium chloride dissolve in water? The reason it dissolves is because of ion dipole forces of attraction. Sodium chloride is an ionic compound, water is polar. So you have ion dipole forces of attraction. In order to get any solid material to change from a crystalline phase to a liquid phase, or from a crystalline phase to a separate atom phase, like dissolving sodium chloride, what do you have to do? You have to take the solid atoms and overcome the attractive forces that hold them together. To melt ice, you have to overcome the attractive forces between water molecules. To melt copper, you have to overcome the attractive forces between copper atoms. To bend copper, you have to overcome the attractive forces between copper atoms. To dissolve sodium chloride, you have to overcome the attractive forces between sodium ions and chloride ions. Why does water do that? Water is very polar. If you look at the energy diagram of sodium chloride solid, liquid water, and you combine them, you find out that the attractive force between a sodium ion and a set of water molecules, not just one, but about 8 or 9 of them, and the attractive force between a chloride ion and the water molecules is greater than the attractive force between a sodium ion to a chloride ion. Now think about that crystalline sodium chloride again. If I take this solid sodium chloride and I want to get it to dissolve, and I put water on the top, I'm only interacting with that top layer of sodium and chloride ions. They behave differently than the ones in the middle. And so that top layer, the attractive force between the water molecules and those sodium ions and chloride ions is going to be strong enough that you're going to rip off a sodium ion. What happens when you rip it off? You've got new chloride ions underneath. You can rip those off and it just slowly erodes away, slowly being a relative word. This picture here, which they're saying is wrong, shows on the left water, and on the right a mixture of sodium chloride and water. And it appears as though the sodium chloride, the dark spheres, are at the surface of this thing. But the reality is every single cation and anion is completely surrounded by water molecules. There is not a layer of sodium ions. We talked about boiling point elevation and freezing point depression on Wednesday. And we said how the energy of the system increases whenever you put anything into a liquid. The common argument is that the sodium chloride crystals get in the way of evaporation. And that's why the freezing point of water or the boiling point of water changes when you add salt to it. the whole issue comes back to energy. Where are the attractive forces? To get something to go from a liquid to a solid, or from a solid to a liquid, you have to overcome those attractive forces, whatever it takes. So there's the picture of that. Blah, blah, okay. So I kept digging into this thing. I said, hey, wow, this is a cool site. Thank you, Jessica. And who sent it with Jessica? Thank you, Caitlin. The hydrophobic effect does not mean that nonpolar molecules are not attracted to water. What is hydrophobicity versus hydrophilicity? Hydrophobicity is a repulsion of water. Hydrophilicity is the attraction of water. Molecules are either hydrophobic or hydrophilic. And you will hear about this in, what's that class? 214. Bio. And this is a great description because it says, you know what? Most of us teach it to you wrong. We talk about how detergents are hydrophobic. They repel water. And how other things are hydrophilic. They attract water. And it talks specifically about oil. If I take oil and put it into water, you've all seen salad dressing. You take oil and vinegar is just 95% water and 5% acetic acid, so it's oil and water, and you shake them up, and you get a nice salad dressing. But you leave it sit for a little bit, and you watch them separate, and the oil, which is less dense, will float on top of the water, which is more dense. And they will continue to separate. And at the layer between them, you'll often see this cloudy stuff. The cloudy stuff is still some oil that is dissolved in the water. What do you do when you shake it? You break it up. You expose the oil particles to water particles. What do we know about the water? It's polar. What do we know about the oil? It's nonpolar. Why should they mix? Like dissolves like. If two things have the same intermolecular forces of attraction, they are likely to dissolve in each other. If they have different intermolecular forces of attraction, they're likely not to dissolve in each other. What are we talking about? We're talking about my favorite topic, energy. In order to get things to dissolve, you have to overcome attractive forces of the forces of attraction that are holding it together. Oil doesn't mix with water. However, if you take one drop of oil and drop it in a puddle, what happens? It spreads out. You've all seen gasoline spread out all over the driveway. Well, if oil doesn't mix with water, why doesn't the oil just stay as this round sphere that it's attracted to itself more strongly than to the water that you've just dropped it into? The reason it spreads out is because the attractive force that holds oil in a droplet is not as strong as the attractive force of water for those parts of oil that are attracted to that. And on the surface, you get different effects. So when you say that something repels water or attracts water, you're not completely right. What you should be saying is that the attractive force for this compound and this compound is greater than the attractive force with this compound in itself and this compound in itself. If you remember back to physics days when you studied momentum, the before, two cars coming down the road, barreling at each other, a Volkswagen and a truck at 90-degree angles to each other. And the after, I could ask all of you, if you've got a Volkswagen and a truck coming at each other like this, you could all tell me they're going to end up over there because you remember your inelastic collisions from conservation of momentum in physics. If you don't, I'll be happy to show it to you again. Anyway, when we talk about dissolving things, the before picture is oil, water. They're bonded to each other. The attractive forces of oil are very strong. The attractive forces of water are very strong. The after, the oil is mixed with the water in some way, shape, or form. Now the attractive forces between the oil and the water are stronger than the oil and water attractive forces. It's all energy that we have to look at. It will become a theme that you're going to see more and more this semester. So, again, thank you for this, because now there's this great picture at the top. I see Caitlin and Jessica, you didn't think I was going to do this much with this, did you? Look at that picture. What is that? It's the international no symbol, right? Other than the fact that it's yellow instead of red. What's that thing inside it? I like his description. Click on the symbol for an explanation of this. Be very, very careful about what you put into that head because you will never, ever get it out. Correcting misconceptions is a really tough thing to do. That symbol is an image of a raindrop, but it's completely wrong. Every single teardrop-shaped raindrop that you have ever seen is wrong. There is no such thing as a teardrop-shaped raindrop. I'm sorry if I'm bursting all of your kindergarten-held opinions. And you go back and look at the picture that Mom saved from kindergarten. We had the nice big teardrop raindrops. They were all wrong physically. Raindrops are spherical. You can do the calculation mathematically to show that if you want to minimize surface area, and if you were just in the talk in the bubble talk recently, they talked a lot about minimizing surface area, you take a spherical shape. Raindrops take a spherical shape. And you say, wait a second, no, hold on, I don't believe you. Raindrops are falling. They still take a spherical shape. Well, if they're falling, what happens to them? Well, there's a bad rain page here. I had fun with this when I got this email. I do read your emails. On the bad rain page, you find out, as they describe them, that raindrops, when they get bigger, don't look like teardrops. They look like hamburger buns. Again, go back to your physics. Draw the free body diagram of a raindrop. What are the forces acting upon a raindrop? There's gravity pulling it down, and there's drag pushing it up. And as long as gravity pulls it down and drag pushes it up and they're balanced, you will get a spherical raindrop. But as soon as the drag is greater than the downward force, it will start to deform to give you that hamburger shape, number 3 there. That's what real raindrops look like. And he goes on to say, if you keep going, wait a second, I don't believe you. I doubt you tremendously. What is the evidence? As scientists, we rely upon evidence. If you were here yesterday, one of the things you heard from Professor Hoffman is that one of the true strengths of science is that everything I tell you in front of this class is subject to debate. I'm not telling you anything that one of you someday may come back to me and say, you're full of S. And here's why. As long as you bring me evidence, I'll listen. Science is all about taking the data you've got and looking at the evidence and from that going. So who do you trust? Your teacher who says that raindrops are teardrops? Or you who says that it's spherical? Well, he says, if you go on and you look at photographs of raindrops, which is something that you can indeed do, you find out that you'll never find a teardrop-shaped raindrop. In all the pictures that have ever been taken of drops, they've never been teardrop-shaped. So that's one piece of evidence. Second, if you do the calculations and you figure out how much energy is there in a teardrop shape, you find out it's a lot. Third, rainbows. Uh-oh, now we're bringing rainbows in this. You can't get a rainbow if you've got a teardrop-shaped raindrop. You have to have a sphere. The bow that you see is a result of the spherical nature of raindrops. If it were elongated, that bow would never show up. So the fact that you can see rainbows is evidence of this. Radar. Uh-oh, now we're bringing technology in. If rain is big drops, as you saw, the bigger the drop, the more hamburger-shaped it was. They now have radar that's going to look at raindrops this way and this way. And they find out that if there's a difference in response from the radar, it's because the raindrops are not spherically shaped. If they're not spherically shaped, they're big. If they're big, it's raining pretty darn hard. And so that's how they can tell you how fast it's raining in real time. Doppler weather radar, right? What is Doppler radar? It checks it in both directions. Well, someone said, hey, I know about terminal velocities. If you throw a cat off a building, at some point they reach terminal velocity, they don't speed up anymore. You've all heard that in your physics class. I know that. Raindrops reach terminal velocity. This is where you get the free body diagram into it again. And the last one says, well, can't I take artistic license? Yes, you can take all the artistic license you want. But if you're a scientist, be careful with artistic license. As you write your term papers, I want you to be somewhat creative. Just don't get too creative. So yes, I can bring this all back to something eventually. I can ramble all I want, and eventually I get it back to something. So, thank you for the email. I do read them, as I said. I'll just close it out of there, although now that I've identified you anyway. Hopefully my voice will hold out the rest of the period, but if not, you'll hear laryngitis coming through. So, where were we? We were talking about, oh, I asked you a question at the end of the period on Wednesday. As you were all walking out, I asked you a question. And I'm going to ask you a slightly different question. Have you ever looked at a cereal box? Yes, you probably have. We've all got a box of cereal, poured the cereal, and then read the box as we're eating breakfast. Every single one of us has done that at some time or another. What does it say about the contents of the box? There's a line on just about every cereal box that says the same thing. Anybody remember? Oh, Thomas has got it. The product in this box may have settled upon shipping. It is sold on weight, not volume. Why do they say that? Because in this litigious society we live in, somebody's going to open their box of Raisin Bran and see 3 inches of air and say, I got gypped. I want a new box of cereal. And all the manufacturer has to say is, what did it weigh? If it weighed what it was supposed to weigh, we never guaranteed you were going to get bran flakes. We just said you would get Raisin Bran. So what if it's crushed on the bottom? That's not our fault. I know it's soggier that way, but that's okay. It's still the weight you need. I was talking with a CFO of a startup company in nanotechnology, and she's got customers complaining now because when they go to take the bottle off the shelf of the product they sold them, the customer is saying, wait, I bought 500 milliliters. Why isn't it 500 milliliters? It only looks like there's 480 in there. And at $15,000 a bottle, I don't want 480 milliliters, I want 500. Why did the volume change? What changed that the customer paid for 500 milliliters, and I guarantee you the company filled the bottle with 500 milliliters of product, and yet when the customer pulled it off the shelf, there's only 480 milliliters.
Is the product they bought denser than the product that they put in the
Is the product they bought more dense than what they put in the bottle? No, they put the right product in the bottle. Temperature, thank you very much. What happened to the temperature? If the temperature goes down on any liquid, what happens to its volume? It goes down. Why? Because as you add temperature, you increase kinetic energy. As you increase kinetic energy, they start moving a little more. Every single liquid will increase in volume upon raising the temperature. It's not a huge effect, but it's enough of effect that it makes a difference. We're about to start talking about concentration units. We'll see if this flips around okay for me. It's upside down? No, it's right side up. Maybe. Well, sort of. Rotate, rotate. There we go. Hit the right button. Is that me squeaking or something else? I'm sorry? It is making, it's squeaking back there. I have no idea what it's doing. And yes, Zach, you will notice a familiar icon on my desktop too, which is why I responded to your Facebook page. Zach knows what I'm talking about. All right. I'm the head scorer for the swim league. Yeah, well, we can talk about that too. This is my daughter's artwork, by the way. This is her playground that she's working on. So anyway, where am I going? I'm going to classes. My daughter has a project that's great. And put yourself in the shoes. You're a 5th grader, and you're given $1 million. And you have to spend $1 million by writing 20 to 40 checks. So she starts building this playground, writing 20 to 40 checks. And I'm looking at her saying, Randy, you're writing $50 checks. We bought tires, we bought dirt. $50 checks are not going to get you a whole long way. So we changed. We now have a $500,000 playground. It's beautiful. So, all right. Where am I? Wrong pen. See what happens when I give my computer to my daughter? Concentration units. Hopefully some of this you've seen before. I know you've seen at least some of it. Oh, she's changed the color on me. This is one we've used. If we talk about the molarity of a solution, its symbol is a capital M, sometimes bold-faced, sometimes underlined. There's no consistency in it. The molarity of a solution is just defined as how many moles of solute divided by the number of liters of solution. What is the solute? What is the solution? The definition of a solute and a solution that I'm going to give you is the solution defines the phase. Solid, liquid, or gas. So whatever determines what phase you've got is the solution. So if I put sodium chloride into water at room temperature, the water is a liquid, and the sodium chloride, no matter how much I put in there, even though it's a solid, will dissolve and you have a liquid solution. If I take carbon dioxide gas and I put it into water, I can make a liquid solution which we call soda. If I take lead and I mix it with tin, now they're both solids. I still have a solution, but now it's a solid solution. Now, if we're talking about solid solutions, we probably aren't going to be measuring the volume of the solution. Instead, we're going to want some kind of a concentration unit that doesn't account for, or that accounts for that fact. So we're going to define a new term, which unfortunately has a very similar name. I have to be very careful when I say molarity versus molality. And the symbol for molality is a lowercase m. What's nice about it is it's still the number of moles of solute in the numerator, but now the denominator changes in two ways. Instead of the total volume of solution, which is the mixture of all of the solvents, or excuse me, all of the solutes with all of the with the solvent. Oh, nobody's correcting me. That's all right. That should be solvent. Sorry about that. You're going to have the mass of the solvent. How much did you dissolve it in? This is a great unit of concentration to use for solid solutions. It's also a great unit of concentration to use if you worry about changes in temperature. Because if you look at the molarity on top, if I change the temperature of the solution, I'm going to change its concentration. Because the volume that you have is going to change as you lower the temperature or raise the temperature. The other concentration unit on the bottom here, molality, when I raise or lower the temperature, the mass of solvent is not going to change. If I start with 1 kilogram of solvent, I'm going to end up with 1 kilogram of solvent. Now, the really challenging part of this is what is the mass of 1 liter of water? How much does 1 liter of water weigh? 1,000 grams, because a liter is 1,000 milliliters, and the density of water is 1 gram per milliliter at 4 degrees C, or 1 kilogram. So now, if I have an aqueous solution, a water solution, and I tell you its concentration in molarity units, moles per liter, will its concentration in molality be the same thing? Will molarity, which is, where'd it go here? Come on, computer, wake up. Moles of solute per liter of solution be the same as molality, which is moles of solute per kilogram of solvent for an aqueous solution? Does it depend on the density? No, it doesn't depend on the density. There is a unit we're going to talk about that does depend on density. I'm sorry? Are they the same? It's very easy to see that they might be the same. For example, Tell me how you would go into a laboratory and make a 4.5 molal sodium chloride solution. The easiest way. How could you make a 4.5 molal sodium chloride solution? Well, the solute is sodium chloride and the solvent is water. I want to make an aqueous solution. So we mix 4.5 moles of sodium chloride with 1,000 grams of water. And if we assume the density of water is 1, how many milliliters in 1,000 grams? 1. 1,000 grams, 1,000. So therefore, it's 1 liter. All right, how would you make a 4.5 molar solution of sodium chloride? Dissolve 4.5 moles of sodium chloride with a liter of water. Thank you, Zanny, I set you up. You know what you did. What'd you do? It's moles of solute divided by liters of solution. When I mix a liter of water with 4.5 moles of sodium chloride, will the final volume be 1,000? No, it won't. When you want to make a molar solution, and the book is very careful to say this, it would say mix 4.5 moles of sodium chloride with enough water to make 1 liter. How much is enough water? I haven't got a clue. What's new, right? I haven't got a clue because sodium chloride interacts with water in a certain way. If I ask you to make a 4.5 molar solution of calcium chloride interacts with water differently than sodium chloride because of the charges. And so the amount of water I need is going to depend upon what I'm mixing with it, but also what temperature I make it at. Because the volume of the water is going to change with the temperature. The volume of the sodium chloride doesn't change with temperature. It's a solid, it's not going to change a lot, but liquids do change. And so you have to be careful because it looks like these are the same thing, but you can't do this. So instead of mixing it with a liter of water, you mix it with enough water. So one of the common questions that will get asked on a standardized exam will be, the molality of a sodium chloride solution is determined to be 4.5. What is the molarity? What is the molarity? How would I get the molarity? I'd have to know temperature because, well, temperature doesn't figure into the calculation, but how does it figure into the calculation? What changes about water with temperature, actually? Not volume as much, even though I've said that a couple times already. Density. Somebody said, don't I need the density? This is a case where you're going to need the density, because the density is going to help you convert kilograms of solvent, kilograms of water, to volume of solution. You need the density of this solution to say, I can't do this unless you tell me that it's a 1.05 gram per milliliter solution. So if I go on to tell you the density is 1.05 grams per milliliter. Now what I can do is I can say, okay, let's take 50 grams of the solution. I can figure out the volume of that 50 gram sample now. And that 50 gram sample, if I know its molality, I can figure out the moles of sodium chloride. There's lots of examples in your book that do this, so you can check that out of there. All I really want you to realize is that they're not the same. They're going to be close. What you're going to find out is that when you compare these two, one of them is just slightly different. The only time it really makes a difference is with large changes in temperature or high changes in density. Then it's going to make a huge difference. The other one, though, is we drew the phase diagram in here. Oh, by the way, that email trail that I was following earlier, it goes on to talk about salt and water and cooking pasta, by the way, and how much the temperature it goes up. If I go down, let me change the color here. Oh, let's do this one. Okay, so the brown curve is the phase diagram that exists for a pure water solution. The blue lines are what happens when I put anything into that pure water solution. And as we were saying the other day, if this is the normal freezing point, then this is the new freezing point. If this is the normal boiling point, this is the increased boiling point. Freezing point always goes down. Boiling point always goes up. There are no exceptions. Yes?
So if you are at a low pressure and you want to go right from solid to gas, from gas to solid, the solute doesn't make a difference?
If you are at low pressures and you want to go a process of going from solid to gas, so a sublime process, does the fact that there's a solute mixed in with it make a difference? It depends on the pressure, obviously, right? If this is the triple point and I'm at a pressure that's down here, I haven't lowered the triple point far enough to change that transition. You will still have the transition from solid to gas at the same temperature. If you happen to lower the triple point below the pressure you're at, yes, then it is possible to make it so it no longer sublimes. So one of the ways that one of the other common, and probably not for you, but for your grandparents, compounds that sublimes very easily is mothballs. Mothballs, when they put them into the closets, would be they were white balls of naphthalene, and the reason we don't use them anymore is because naphthalene is a known carcinogen. But naphthalene would get thrown in the closet, and the naphthalene would vaporize without going through the liquid phase. Well, the vapor is rather poisonous. Moths would breathe it and, keel over and die. If you've ever gone into an attic that had mothballs in it, you knew it. It's got a terrible stink to it. So the same thing would be true there. But let me go back to this for a second. Delta TF. One of the reasons we do this is, remember I asked you at the end of the period Wednesday, why would I need a temperature-independent concentration unit? And one I started to tell you was, if you're selling a product that changes volume on temperature, and you happen to package that product at high temperature, at low temperature it's going to decrease in volume, somebody's going to say to you, I didn't get the total volume, and they're right. But if you look at any liquid that gets packaged at high temperature, like canned tomatoes, they'll always tell you that they're sold by weight, not volume. And they have to be canned at high temperature so as to kill bacteria. And then when they compress, and you all know that because when you open up any canned vegetable, what's the first thing you hear when you squeeze the can opener? The whoosh of the air going in to replace the vacuum that's in there. You've lowered the pressure in there as it cools, and the volume will have decreased too. There's a nice, simple relationship between the freezing point change and the concentration of what you've got. The change in freezing point, the delta TF, where delta TF is TF minus the normal freezing point minus the new freezing point. Or you can do it the other way. I can never remember which way people want to do it. I always know freezing point's going to go down, so I don't worry if it's positive or negative, since I always know it's going to go down. Well, it's equal to some constant K times the concentration. Well, that makes sense. If I dump more stuff in there, I'm going to get a bigger change in freezing point. So it's directly proportional to the amount of stuff that's in there. And we need a concentration unit, M, that doesn't depend upon what the temperature is. Kf, that constant, it's a fudge factor. Or, for those of you who prefer, if I plot concentration and change in temperature on freezing, it's a straight line, and the slope is Kf. So that's the way you get these constants. The problem is that the freezing point depression constant, which is what that's called, depends upon the compound, not on the solvent. It doesn't depend upon what you put into it. It only depends upon the solvent. So water has a freezing point depression constant. And it doesn't matter if I put salt, calcium chloride, crushed glass, sand, shredded up pieces of paper, anything that I put into water will lower the freezing point based upon the freezing point depression constant of water. How far? Right there? Kf is a constant. Kf is called the freezing point depression constant. And you would have to be given that value. A classic physical chemistry experiment that you do as a junior is to figure out what the unknown concentration of a compound is by measuring how much the freezing point goes down of a pure liquid and the liquid with that solid dissolved in it. The problem with that experiment is in order to get good data, you want something that you don't need a very large concentration, because once you get to high concentrations, I'll try to bring you a supersaturated solution so you can see why high concentrations are bad. But if you keep concentrations low, so M is a small number, the change in freezing point is small unless you have a freezing point depression constant that's large. Well, guess what kind of compounds have high freezing point depression constants? Carcinogenic compounds. And so when I was doing these experiments, I'm breathing in all these carcinogens, which may explain why I am what I am today, but I doubt it. There's another simple equation here that looks very familiar, which says that the change in temperature of boiling is equal to a constant, Kb, which is just the boiling point elevation constant, times the molality. So it's exactly the same equation. It's just now we need a different constant. And you would have to be given those constants. There's no way to derive them from basic principles. All you really need to remember about that, and I'll make sure you get a sample problem like it, is that diagram. If you mix something into a pure liquid, you shift both of those equilibrium lines down. The solid liquid equilibrium goes down, and the liquid vapor equilibrium line goes down. And because they both go down, the freezing point of a mixture is always lower than the freezing point of the pure liquid, and the boiling point of a mixture is always higher than the boiling point of the pure liquid. The best and most enjoyable example of this is ice cream. What do you have to do to make ice cream? You take that big can and you pour the cream and the sugar and the eggs and the fruit or whatever you're going to put into it into the metal can, and then outside it, what do you put? Salt and ice. And why do you put salt and ice? Because you've got to lower the temperature below the freezing point of pure cream, because now it's not cream, it's cream with sugar and fruit and everything else in it, and so you've got to get as low a temperature as you can. How low a temperature can you get with salt and ice? This was a trivia question from last semester. What's the lowest temperature you can get when you mix salt with ice? I'm sorry? 0 degrees Fahrenheit. Very good. 0 degrees Fahrenheit is as low as you can get when you mix salt and ice. That's how the 0 degree set was set on the Fahrenheit temperature scale. Monday, hopefully, I'll show you why you can't get below 0. I will see you Monday. Have a great weekend. Thank you. You're welcome. Come again anytime.
Okay.